In this video, we prove by principle of mathematical induction that a to the power 2 to the power n is congruent to 1 mod 2 to the power n plus 2 for an odd integer a and positive integer n. Let us prove by principle of mathematical induction. Of course, when we say principle of mathematical induction, we must show that base case is true or starting case is true, and then we must show some kind of recurrence relation is true. Let's show that base case is true. We are said that n is a positive integer, so n should start with n equal to 1. So for n equal to 1, comma a to the power 2 to the power n is congruent to 1 mod 2 to the power n plus 2 if we just need to write n equal to 1. So a square is congruent to 1 mod 2 cube, that's 8. So we just need to show that a square is congruent to 1 mod 8, whereby a is odd. That is if a square minus 1 is congruent to 0 mod 8. Now a square minus 1 can be factorized, and we can write it as a plus 1 times a minus 1 is congruent to 0 mod 8. In other words, a plus 1 times a minus 1 is a multiple of 8. Observe that a is odd, then a plus 1 is even, a minus 1 is even, so a plus 1 times a minus 1 is a multiple of 4, but we want it to be multiple of 8. We know that for any integer a is congruent to 0, 1, 2, 3 mod 4. For any integer a is congruent to, once again, for an integer a is congruent to 0 or 1 or 2 or 3 mod 4. So what can we say for about odd integer a? If a is odd, a cannot be congruent to 0 mod 4, a cannot be congruent to 2 mod 4, so a has to be congruent to 1 or 3 mod 4. Now if a is congruent to 1 mod 4, if a is congruent to 1 mod 4, then a minus 1 is congruent to 0 mod 4. So a minus 1 is a multiple of 4. But we know that a is odd, then a plus 1 is a multiple of 2. Multiple of 2 times multiple of 4, the product is a multiple of 8. What if a is congruent to 3 mod 4? If a is congruent to 3 mod 4, then a plus 1 is congruent to 0 mod 4. So we see that either a minus 1 or a plus 1 is a multiple of 4, but the other one is multiple of 2, so the product is multiple of 8. So in any case, a square minus 1 is congruent to 0 mod 8. So the base case is true. So far we have succeeded in showing that base case is true, or the given statement is true for n equal to 1, or the starting point is true. Now we want to get some kind of cycle, that is a to the power 2 to the power k plus 1 is congruent to 1 mod 2 to the power k plus 1 plus 2 whenever a to the power 2 to the power k is congruent to 1 mod 2 to the power k plus 2. So it is true for k equal to 1. From there we want to conclude that it is true for k equal to 2. So we assume that a to the power 2 to the power k is congruent to 1 mod 2 to the power k plus 2 for some positive integer k. Then a to the power 2 to the power k plus 1 minus 1 equal to a to the power 2 to the power k times 2 minus 1. That's equal to a to the power 2 to the power k whole thing square minus 1 square. That's equal to a to the power 2 to the power k plus 1 times a to the power 2 to the power k minus 1. By our induction assumption, a to the power 2 to the power k minus 1 is a multiple of 2 to the power k plus 2. And as a is odd, a to the power 2 to the power k is odd, and odd plus 1 is even, so this is even. And so the product is a multiple of 2 to the power k plus 3, that is a to the power 2 to the power k plus 1 is congruent to 1 mod 2 to the power k plus 3 whenever a to the power 2 to the power k is congruent to 1 mod 2 to the power k plus 2. Now when we choose k equal to 1, we see that a square is congruent to 1 mod 8. That implies that a to the power 2 to the power 2 is congruent to 1 mod 16. Again, by choosing k equal to 2, we will see that it is true for n equal to 3. Again, by choosing k equal to 3, we will see that it is true for n equal to 4. Hence, by principle of mathematical induction, the given statement is true for every positive integer n.